Okay, good morning everyone. Thank you. Good morning. So welcome to the last day. So I have the pleasure of you this morning. So I'm going to talk to you about landslides. Landslide field reconnaissance and also use of remote sensing for monitoring and looking at deformation. I'm then going to give you a short introduction to the Sano exercise that you do. I'm going to show you the data and talk through what the landslide event was, and then talk through the practical activity, and then need to look at some of the mitigation they put in place. Okay, so that's the plan for the next hour. So we're going to look at a big landslide in the French Alps called Himalaya, which you looked at in the virtual reality. Yeah, so a really big landslide looked at in VR. I talked briefly about. This is a more detailed overview of it, and then some work we did on monitoring it using some remote sensing. It's a very interesting site because it is a mixture of bedrock geology and quaternary geology. It's at the front of a glacial snout and has a whole series of geological units that are being involved really in the landslide movement. So my presentation will cover where the landslide is, look at the deposits, the geology, a quick overview of landslide processes just to remind you from my first lecture last week. Geotechnical behaviour, so just some things about the geotechnical, the material properties and how they impact the slope. And then I'm going to go on to the methodology and how we looked at the landslide displacement and then just some results. So study area. So study area is here, just south of the city of Grenoble. Grenoble's here. This is the Drac Valley, and the area is here, basically around the town, as I showed you, of Synod. Here is a Google Earth image of it. You recognise it from the virtual reality. So Synod's town is here on the side, Avignon is here, and Himalaya is this catchment here we saw, and we can see very clearly here that there's evidence of instability. This river here is the River Drac. There's been, you can just see the top here. There's a dam. It's been dammed for hydroelectric power generation, and it's a very nice lake to go onto. Here's a three-dimensional view of it, looking at the valley. So there's the town of Synod again. Here's a landslide in Himalaya, slide the catchment we're talking about. Here's the reservoir here, but do notice that that's just an artifact of the data. So as I said earlier on, just to you've got these steep aligned ridges, these Jurassic limestone mountains, but all of the lower bottom valley, the flat valley here, is all in these quaternary deposits, these glaciers. So the whole of this valley here was essentially filled with ice, okay, during the recent ice advance. So talking about that ice advance, here it is. So here's Grenoble at the top. If you go back 18,000 years, this is what it must have looked like. So you would have had a large glacier, valley glacier here, filling in all of these, most of these valleys, essentially outwashing. And then I mentioned that there is the formation of this very large lake, Lac de Truyère, which is formed basically because the water coming from these glaciers had nowhere to drain, and so therefore formed this very large lake. So the deposits we see from this are things like glacial tills, I'll come on to shortly, moraine deposits, fluvial glacial, so that means fluvial means water, so river systems from glaciers, glacial lacustrine means lakes, so that means lakes formed by glaciers, as you see here. And this deposit here, when they drilled it and did some geophysics, was up to 300 kilometers squared and about 250 meters deep. So a very thick sequence of these clays which are infilling these valleys. So when we're talking about applied geology, we talk about a ground model, and a ground model for us is a conceptual model about the kind of conditions that we anticipate, and with it the kind of geology processes that we might encounter. So this is from like a sort of a school textbook, but you can see here the glacier here. You've got some push moraines, you've got lateral moraines, you've got the till, the lodgement till, which sits beneath. Okay, we've got nullattacks, which are these peaks which are undergoing mechanical erosion rather than during the freezing and thawing. You've got these fluvial, these river outwash deposits, sediments coming from the front of the glacier, and then sometimes lakes also form in that frontal zone. So that's what we term like we call it a conceptual or geological model. If you kind of look at a contemporary kind of environment and think about what it would look like, this is the kind of conditions it would have had going back 18,000 years. You can imagine glacial snouts, large lakes forming, loads of debris, fluvial deposits coming out, large moraines, but also the glacier is not static. The glacier is advancing and it's retreating. It's advancing and it's retreating. So it never stays in one place for very long. Okay? So even during times of stasis, it is waxing and waning. There's lots of moraines, there's lots of debris coming in, etc. into the system. So it's a very, very dynamic environment. Okay? And now, when you remove that glacier and come forward in time to us, we're left with the ground conditions, which we term are highly variable, are very, very difficult, and quite susceptible to movement. Then what's happened, if you can imagine the glaciers disappeared, is the river system's re-established. So the drainage occurs, the rivers forming, and then they start to form in these valleys, and they start cutting through and eroding to all these deposits. And as a result, the slopes start to get unstable. In terms of the geology we see here, this is the kind of sequence that have been produced by some of the local researchers. So the yellow colours here are the Jurassic bedrock, these limestones. But you can see here that what they've got here are essentially glacial tills, varve clay, these lake deposits, and then fluvial outwash, these fluvial outwash deposits. And you can kind of see the thickness of them, from about 900 down to about 500 metres. So in total, up to 400 metres thick of highly variable deposits. So this is the landslide we're talking about, Himalaya. Okay, and during the virtual reality, I said you need to find at least 3 other landslides. Okay, so the first one was the Avignon landslide. The second one hasn't got a name, but there's also an relic landslide here, and there's also another landslide over here. So actually the whole series of them, of which Himalaya is the most obvious and most active. So here at BB, you can see here, which is this low one, you can see here the deposits here are about 200 metres thick, alternating between varve deposits and also these outwash channels. And I'll show you some examples of these in some photographs shortly. What I'm going to do is I'm going to work up the sequence. I'm going to start at the bottom, and I'm going to work up the sequence to show you photographs of each of the different formations. If we start at the bottom, so here we can see some nicely dipping Jurassic limestones, and then we can see a very sharp unconformity here. I think I've got that marked. Oh yeah. We can see these very nicely horizontally bedded, essentially coarsely grained sands and gravels. Yeah, very clear, distinct coloration. So that's the bedrock, and this is the start of the fluvial system that's beginning to infill. So the glacier is arriving, it's coming in, it's outwashing, lots and lots of material, and that material is beginning to deposit in front as the glacier advances. You can see it all the way along. Again, you've got dipping limestone, you've got again these horizontally bedded gravels and sands, which are really these outwash deposits from these rivers. what's interesting is that these river systems completely infilled an existing undulating topography. So you can imagine this limestone here is quite undulating topographic surface, and essentially it's been infilled, all that talk has been infilled by all these channels as they begin to move around. So what they look like, so my colleagues at scale, just to show you the grain size, very large cobbles here, clearly aligned to some imbrication, some stacking of the clasts. I've got a close-up, I think it shows you, again, the size of them. So very high energy. If you want to move some of these blocks, you need quite high energy, you need quite rapid running water. Here, this is to kind of show you the imbrication. Imbrication is where, I'm assuming, where you get stacking of the clasts as the water flows. The clasts tend to stack and lie on top of each other. So you can kind of see, if you get your eye in here, there is some stacking of the clasts as a result of the water flow. So it's clear. So then what happens is suddenly, these are all these river deposits, these high energy deposits, and then suddenly there's a change. Suddenly that completely stops. And then we move into these very fine-grained, laminated, you can just see the laminations here, these fine-grained laminated deposits, these varve clays. So you go from an environment dominated by river systems to an environment dominated by lakes. Okay? And essentially, most of what we're talking about today is made up of these lake deposits. Again, don't forget, about 250 meters thick of this. So it's very thick. So this photograph is a view down that valley, and it's designed to try to visualize what that lake might have looked like. So, so the varve clays, this is the lac de Montagnard here. The varve clays essentially come up here to this ridge here and come to this line. So if you follow this down, you can kind of see where the lake would have been. Yeah. So all those fields are essentially lake deposits. If you look, you can look down and see how extensive this lake would have been, all the way down south. It's very extensive. Quite complicated processes taking place as the ice is carving into these lakes. You get a series of sort of turbidite deposits forming here. You're getting a series of drop stones. You're getting sediment coming out of suspension. So actually the formation of these varves is actually quite complicated. And so you get rhythmites and varves. You get homogeneous clay, very thick deposited clay as well. So as the ice is then carving these ice into these lake deposits, the processes of the formation of varves is quite complicated. So what they look like, essentially very fine-grained laminated clays, essentially break off as a series of, you can see here, a small series of slabs along these laminations, very fine-grained. You can see evidence here of these turbidic currents, these scouring surfaces on some of the basal units in response to some of these processes we've talked about. And again, you can just see, in some cases, very thick, homogeneous clay, and in some cases, very thin, laminated clays are present. So again, very. And those are formed from these lakes, essentially, just very, over long periods of time, just sedimenting out of suspension. We then move to the top of the sequence, as I said, all the varve, and we start moving into essentially tills, essentially homogeneous clays with classing of host rock, no structure, no bedding. So you can see here you've got this sort of till, a little bit of varve clays, till, and then some more varve clays. So we've got ices moving forward, coming back, advancing, retreating. And that's the top of the sequence. So very complicated geology. And again, we can see what I say here again. This is the till. We can see this sort of kind of Dalmatian looking material with these classing. no structure at all. That's your till deposit, and then you've got some clays on, some valves on top, and again back into tills. So you've got quite a dynamic environment taking place. And the landslide is essentially moving in the tills and the valve clays, those lake deposits. So I've shown you the tills. I've shown that we don't see any moraines in this site. We haven't seen any moraines, but we've seen some outwash deposits, those very coarse-grained channel deposits outwashing from the glacier. We've also seen the valve clays, which are the remains of those lakes. And that's all situated here in this site at Synard, at the boundary between the glacial and the proglacial environment. So again, I talked to you before about the extent. So this dashed line sort of approximates where the extent of that lake might have been if you were to try to extrapolate the edge of those clays. Essentially, you kind of get a feeling for how big and how deep that lake was. Again, no overview here. So here's the back of the landslide. We're looking down the valley, and again trying to picture how big this lake might have been. So very, very extensive. Yeah. It sends you all the way down here, all the way down the side, all the way through here, all the way back up again. So a very large lake deposit. So why do we get landslides here? So the first reason is because of the downcut. So the rapid downcutting of the rivers into those soft deposits means the sides become oversteepened and begin to move. What we term anisotropic materials. That means the valve clays are quite anisotropic. They're strong in one direction but weak in another. So they're strong basically perpendicular to the valves but very weak along the valves. So they are quite anisotropic. Also, they tend to shrink and swell, so therefore that tends to be a problem. And also we have what's termed hydrogeological variability. That means that you've got some deposits which allow water to move through them easily and some that do not. Okay? And that results in preferential water movement, perched water tables, and an increase in pore pressure, which causes landslide. So types of landslide we'll see are translational, rotational, and flows. And I showed you some photographs of these earlier, so I'm not going to spend too much time on this, but essentially, like we showed you, the big rotational failures, classic ones here, you see at the back of the landslide. Each block is moving at a size about between 1 and 2 meters in size, and that's a typical retrogression rate of this landslide. I showed you again the step nature. You can see it's nicely stepped. 1, 2, 3, 4 different steps from those multiple blocks. There's multiple rotational landslides. Got some translation, which is where the blocks are just moving out horizontally. These ridges here are remnants of this translational motion as they begin to translate out. And then flows. So I'll show you this. Classic flow here, big source area, channelized, and then basically a big low down below. So back to this image. So we know now that these mountain ridges here are the Jurassic limestones, okay, and we know that this valley here is infilled with those very coarse-grained channel deposits, those gravels and those cobbles. You've got laminated valve lake deposits, very thick, and then also tills. And then essentially what we see here, this whole sequence is dominated by the valve clays and those till deposits. And so the landslide is moving in those deposits. So if you go back, the French have very good archive photographs. I went back to 1948. I went and looked at every photograph since, regularly. We also rectified them, so we corrected them for distortions, made them sort of like maps to try to do comparisons. And you can see very clearly here, 1948, there's not a lot of evidence of lots of movement. Obviously in 2003, it was moving quite a lot. But I think we've talked about there is a little bit of, in we term incipient movement, a little bit of erosion and some evidence of some small scale movement taking place. We can generate these, which are anaglyphs, which I won't go into. What we did do is look at all of the photographs, also rectify them to look at the data, and we also had LiDAR data. So LiDAR, you know what LiDAR is? LiDAR? You're a tough crowd. LiDAR, you know what LiDAR is? Yes, no? Yes. Good, excellent. I like that. So LiDAR is essentially acquired from a plane using a laser and gives you a very accurate topographic model. So here we can see the landslide, okay? We can also see the dense vegetation, the trees. We get a good idea of the landslide. We can also see these scarps here from the motion of this side of the catchment also into the valley. Bit difficult. What we can also do is we can also remove the vegetation. So some colleagues in Grenoble had some LiDAR taken from a helicopter, and they've used the last return to strip off the vegetation. So that's with vegetation, that's without vegetation. And you can see that actually the landslide itself is a very small part of a very, very large movement. Actually the whole catchment is moving, not just the bit that we can see. The model for it, essentially we've got very deep-seated failure in the Var clays, okay? And then a series of superficial, shallower failures. So basically we've got everything. We've got big, deep-seated failures, and we've got shallow, translational, and then also shallow flows. So pretty much I've seen all types of movement in this landslide. So the model we generated was this. So we generated, so if you let me go back a slide. So we subdivided the landslide into two zones. An upper zone and a lower zone. An upper zone that was dominated by the rotational movement, and a lower zone which is dominated by the flows. And you can see that in the photograph. If I go back two. Okay. You can see this lower part is primarily moving, is primarily flowing down, and this upper part is primarily sort of failing as a rotational failure. And so in our analysis we were able to work out essentially what the zone was, what the boundary was between the two, between this rotational zone at the top, and then this zone where we've got dominated by flows down. So what we did was we wanted to try to monitor the landslide. We wanted to try to see if we could work out how fast it was moving and which way it was going, which is quite challenging because they have very little GPS data because it's quite a dynamic environment. So we used a process called digital image correlation, where we used essentially aerial photography and photogrammetry to try to do what's termed image matching. It's quite a good technique where you've got images of the same area taken at different times. So we used photographs. So our photographs are stereoscopic, so they overlap each other. And essentially we were looking at using stereo photographs. And essentially the principle is this. So we have two images of the same place, okay? Two photographs. One is the pre-event and one photograph is post-event. Do you like my graphics? I did these myself. Thank you. Yeah, it took me a long time. Okay, so I'm rubbish at doing these. Anyway, so this is the pre-event. There's no problem. Nothing's happening. Okay, the house is there. Everything is fine. An event occurs. My landslide scarp. Oh, sorry. That's my mother. How embarrassing is that? Okay, so here's the scarp. Okay, my scarp and landslide. And essentially what's happened is 3 of the trees in the house have moved down slope. Okay. And what we want to do is I want to measure how far that house has moved and in which direction. Okay. So what we can do is we can take these images and we can match them together, and then what it does is it tries to find the same feature in both images and tries to work out how much that feature has moved. Okay? How much is the offset? So by comparing the photographs, you can then work out which way it's moved and by how much. It does it by a thing called digital image correlation. Okay, so here's the object before the event, here's the object, so here's my house before, here's my house afterwards. It's moved, it's gone from this square here down to this square. And so what I want to do is basically work out, it was there to start with, it's moved to there, which way has it moved and by how much. And it produces a delta y, delta x movement amount and a vector of motion. It does that by using what's termed image comparison. It basically takes your object and then searches for it in a search window to try to find it. Okay? So it goes to your earlier image, your first image, finds the object, goes to the next image, tries to find it. When it finds it, it's got it. Okay? And then it has a location to start with, a location at the end, and can work out which way that feature has gone. It does require ortho-rectified and geo-corrected data. So it's got to be ortho-rectified and geo-corrected for it to work. So we did it using photographs from the French mapping agency. You need GPS ground control. Image couplets, I mean, need 2 photographs, one before, one afterwards. So we used 2 sets, 97, 2001, 2001 and 2003. And then if you ever used our photographs, each set of our photographs comes with a camera calibration file. So each camera in the photograph, in the plane, is calibrated. You need that calibration file for your sets of photographs. Luckily, the French mapping agency were very helpful. They just sent us the PDF files of that information.
So what is the method to rectify the Meridian photo?
To rectify?
Yes. Do you use ArcGIS or something?
We used what did we use? No, we use DAS Imagine, and you have to have a topographic model.
Okay.
So you have to correct the data for the topographic distortions as well. So it's not just about using GPS locations. You need a GPS location, which we had. You also need a topographic model to correct the image for the topographic distortions. So it's a full geo-correction. Okay. So when we did this here for the photographs, you need to input the GPS locations. You also need to have an elevation model to do the full geo-correction. Okay. I think most packages will do it. Essentially, you probably would need a full image processing package, which ArcGIS really isn't. So essentially, you've got two set images. You do identical things to each of them. You rectify them, you correct them, and then basically you compare them. You do the correlation. So one image before, one after, and you do a comparison. So I'll come back to that. Okay, so what we did was, so here's the photographs that we used. Here's the elevation model we used. So actually what it's doing, it's trying to match every single point in your image. Not just one. It's trying to find objects and then trying to identify which way they've gone. You can define the kind of size of the object it looks for, but then it produces a map of where those features have gone. So we did that for the 2 epochs. Here's the first set, and it gives you essentially running with the amount of movement taking place. How has it changed? Okay, between whether it's gone up or down. Red is up, blue is down. Okay, and then you've got in terms of the arrows, it gives you essentially a sense of motion which way it's going. So we can see here the landslide here. We've got an area here of accumulation. Essentially what we've got going on there is we've got blocks failing. and we've got material being added. Okay, and then here we've got a zone here of where landsliding is moving downslope and being lost. We've got some areas here where we've got some new landslides taking place, and so therefore getting accumulation of material as a result from the upper slopes. So that is, which epochs are those? 98 to 2001, then 2001 2003, we did the same again. We've got some very clear motion here on the scarp for the landslides. What was most interesting is we've got areas of what we term, you can see this speckling here, that's decorrelation. That means the image was not able to correlate between them. And the reason for that was because there was a brand new slide, which I think I'll show later on. Yeah. So basically, between the two landslides for a period, there was two massive failures on the flanks, which was not there beforehand. So therefore, it couldn't find a similar feature because there was nothing similar. Because this is brand new, you can't correlate them because they don't exist in this image, and so it decorrelates, which is quite interesting. So we've got decorrelation in these two areas where the landslide just freshly moved. And we can see clear evidence of motion here in some of these scarps, but less of motion on the upper part of the landslide. So it worked quite well. We got some good results. It's quite tricky to do, but it was quite successful. We also did some photogrammetry. So we took different epochs of imagery, and we basically generated elevation models, and we then looked at the change over time. So let's get it 93, 98, 2003. So what's quite interesting is that the upper part of the landslide is decreasing, essentially it's losing material, and the lower part of the landslide is getting new material. So basically, this material is moving on down the landslide. So we're able to calculate the volumes of materials that are being lost and being gained by the landslide. So we thought it's been done quite a lot for glacial environments. It's not been done a lot for landsliding. So we thought it was quite a good technique. We can't verify it because we've got no GPS data, but we verified it from image interpretation. And what we did show was that you can't have your image couplets too far apart. Why is that? So if you have, I can't look at a landslide in 1995 and then look at it 20 years later. Why not? Don't forget it's looking to match features. Will features still be there in 20 years' time? Probably not. Because landslide has moved on, everything's changed. So we found that you could look at a landslide about 3 years in the future, maybe 4 years, but beyond that you couldn't look at it because it changed so much you weren't able to find similar features. So that was it really. Really good science, lots of fantastic geology and landslides. So that's my lecture. Thank you.